Okay, chapter 12, linear kinetic movement. Here's what we would like to do today. We're going to talk, Newton's laws of motion. We have 3 of them and the gravitational law of motion. I'm going just to go through them quickly and I'll tell you what kind of applications we are going to be using. What kind of applications are there using these laws that are important for biomechanics. Then we're going to touch base on friction again. I know we covered this in statics and dynamics, but there is another friction that we'd like to talk about. And also we're going to talk about impulse, momentum, and explain the relationship between the impulse and momentum and how they are important, especially with contact or body contacts. And that's important in biomechanics. So quickly, law of inertia is Newton's first law, right? And we know that a body will maintain state of rest or constant velocity unless acted on by external force that can change that state. We agree on that, right? Okay, can you think of a biomechanics example from sport? Yes, no, maybe so. So if you ice skating, if someone pushed themselves, they will continue going. But let's say that's one of them. That's absolutely correct. Yeah, that's a good one. Now, how about when someone is, let's say, playing basketball? Can you think of something in basketball? Yeah, or so not shooting. So let's say someone is trying to do defense and someone's trying to run across him or her and then they collide, right? Something is stopping the movement, right? The velocity, right? That's one of these. You can think of that as an example. Yeah, so the things that I'd like to look at the inertia, but I like the skating, curling, that's all good. Now, that's an example. So this is a skater, has tendency to continue gliding with constant speed and direction because of the inertia. We have very little friction. Does it make sense? To make inertia continuously move. Good. Now, law of acceleration. What is the law of acceleration? F equals time mass times acceleration. It's a force applied to the body causes an acceleration of any body, right? If you apply a constant force. And what happened is that the magnitude is proportional to the force in the direction of the force, and it's inversely proportional to the body mass. Make sense? We're talking about the acceleration. So if you took the acceleration on one side and you have force divided by the mass, the acceleration is inversely proportional to the mass. We good with that? Cool. And now, the law of reaction. For every action, there is an equal and opposite reaction, right? This is one of the most important laws actually we do in biomechanics. Because remember the force plates? Everything we were measuring, it's a reaction force, ground reaction force. That's what it's called. And that's how much your body is exerting on the ground, and the ground is returning it back. When one body exerts a force on the second body exerts a reaction force that is equal in magnitude and opposite in direction. Now, remember this graph that we said that this is a typically ground force for a step, and we said that you can tell if the subject, so this is ground force pattern over rear foot strikes and others, and you can say that this is the solid one is the rear foot strike, correct? The dashed line is the midfoot strike. You don't want to have a rear foot strike. Does it make sense? Because that's a large collision and impact. That's tricky. But you can tell from the ground reaction forces that about the subject, is he or she doing rear foot, midfoot, or forefoot, and that could be of a clinical value. Now, especially in biomechanics, where do you think this is really, really valuable for us? Normal subject, healthy subject, it's fine, right? We can get the data, we can analyze. But when someone has an injury, that is actually really valuable, especially ACL tears. In ACL tears, when you do the surgery, the foot behavior actually changes. Remember, our body is a 3-dimensional multi-segment coupled. The coupling is the thing that can affect the foot if you have surgery in one of the joints. Does it make sense how we're looking at that? Cool. So you know how to operate the force plate. You can design an experiment. You can collect data. We can study, let's say, the effect of ACL surgeries on the foot pattern or the ground reaction forces of the foot. Cool. Now, in accordance with the Newton's third law of motion, ground reaction forces are sustained with every footfall during running. Do you know what does that mean? What does that mean? You should actually reproduce the same patterns. Because your body is in running and you're doing cyclic load continuously and repeated. You're doing repeating. Like walking. Walking is a repeated process. So you can study, here's the thing, coordination and skill can be studied actually by looking at that. But we need to have a treadmill that has the capability to measure reaction forces. Does that make sense? Our 2 plates are then going to be helpful for someone who's doing running or sprinting of that thing. It's a thing. You can identify parameters by seeing how symmetric each step actually during running, because your body will select an optimized pattern to do that until you feel tired. And then you have something different. And that's another thing that you can quantify, actually. Okay, that's good. Now, better sprinters are able to generate forward direction horizontal component. And to do this, you need to lean forward, right? And there is a specific configuration of the body in order to be able to generate that much force. Remember, on the force plate, how many forces we can measure? 3. The vertical one is for vertical jumps, but the X one is the one that can tell you how much a sprinter is actually pushing forward. And you need to go as quickly as possible. And that means larger forces on a short period, in a short period of time. And that's called momentum. We're going to talk about it later on. Does that make sense? So the F horizontal, which is the Fx on the force plate, is the one that can help identify the forward direction. So I'm trying to connect these basic laws with biomechanics quantities that we care about. Make sense for us? Cool. Now, there's something also that Newton had created or formed, the law of gravitation. Now, because we are very close to the ground surface, that's not a big deal for us. But when you have bigger and bigger objects like planets and stuff, that's a big issue. So even this chair, see this chair and myself, or this table, we are exerting gravitational forces. But it's very minimal because the gravitation factor is really small, right? And the masses are small as well. So you don't feel the force, but every single object is actually attracting or exerting force on another object. So all bodies are attracted to one another with forces proportional to the product of their masses and inversely proportional to the square of the distance between them. And you have the G factor, which is really, really small. I think it's 10 to the power minus 3 or something like that. But I have to check what that is. Friction. Now this is the fun stuff. You remember so friction, we have the formula for friction. It's a force, correct? So when we learned about statics and dynamics, we learned about the different types of force. Can you name 4 different forces that you learned in statics? No. Friction is one of them. That's for sure. What's that? Normal forces. What is that called? Reaction forces are the one that you hold these things to and then what you call is an external force. So you have external forces, you have reaction forces, you have also internal forces. Remember the trusses when we cut them and we got the internal forces? That's an internal force. And then you have friction force. What else you covered? Internal, external. Yeah, those are the forces. And then we started formulating equations of motion to solve these forces. And that's what you did in statics. Now, in friction, you learned about static friction and kinetic friction, right? Or dynamic friction. Now, there's another one, a third friction force we'd like to talk about. But before we do this, what is friction? It's a force acting over an area of contact between 2 objects or surfaces, and the direction is opposite the direction of the motion or the tendency to move. Make sense? Now, tendency to move or motion tendency is very, very important in our analysis for 2 reasons. Do you recall what is the formula to calculate the friction force? F equals mu, which is the friction coefficient, multiplied by the normal force. Now, how many coefficients of friction do we have? 2. Mu s and mu kinetic, mu k. The mu s is the static and the mu k is the kinetic. Now, if we are moving, we're going to use the mu k. If the object is about to move or the tendency to move, you just use the ms. You can't use ms unless explicitly stated that the subject or the object is about to move. Does it make sense when we do that? That's important. Now, quantified in unit of forces, it's a Newton, it's a force. And the thing is that the magnitude is the product of the coefficient of friction and the normal friction force R. Can you think of applications for us? So what is the most important friction coefficient, mu, that you need to identify for an athlete? Was that the wearables of the shoes? Yeah, right. And the ground. Is there 2? There should be 2. Because if you have the shoes of different ground, you have different coefficient of friction. That's correct. So you have 2 parts. You're right. So let's say I bought a new shoe and I'm trying to play on the field. Do you know a way or a design an experiment to identify the coefficient of friction of the shoe or the ground? We're going to do this on Thursday. We're going to be quantifying the coefficient of frictions for different shoes on different ground, soles. But are we good with the formula? F equals mu times the reaction force, which is the normal force, N. If you have this object here, and I told you there are no applied forces, no friction, horizontal forces, and no motion, what is the magnitude of R? Yeah, so you need, in order to formulate the equations of motion, you will say summation of forces on X should equals to 0, right? Summation of forces on Y should equal to 0. And I don't have anything that is, and the summation of moments should equal to 0, right? Around a center, a specific point should equal to 0. And then you formulate the equations of motion. Now, also, you can add another equation, which is the force of friction is mu multiplied by R, right? So we keep adding these equations in order to have enough equations to solve the problems or the unknowns, to solve for the unknowns. Now, no, I have only forces in the y direction. So the weight, we assume some going up is positive. So R minus W equals to 0, then R equals the weight, the W. Make sense? Now, here, in accordance with the law of friction, of reaction, the forces acting on the box are its own weight and the reaction force applied by the table. So R is equal the magnitude and the opposite direction of the box, which is the weight. So we're good with that. Now, maximum static friction and kinetic friction. These are the things that we would like to look at. Maximum static friction is the maximum amount of friction that can be generated between two static surfaces. In the problem, I need to explicitly state that the object is about to move. If that's not stated, you can't use the static friction. The coefficient of friction. Kinetics, when things are moving, you use the constant magnitude friction generated between two surfaces. Now, which one do you think will be larger? Static friction force or kinetic friction force? Larger static, right? Because if you push something at the beginning, it's hard, but when it starts moving, it's easier for you to keep it moving, right? Good. Here, a quick description again before we start and solve a problem together. No forces in the horizontal axis. The reaction force equals the weight, correct? Now, if you push with a small force, right? Small force. Now you have friction, correct? But it's still small applied force, small friction force, and that's the relationship between the two. Fa equals Fs. Because all the forces in the horizontal axis should be equal to 0, correct? Make sense? Yeah. Now, if you increase the force, it's going to still Fa equals Fm. But in these two cases, this case and this case, the object is still static. It's not moving. Make sense? So your force is increasing, but it's not moving. So the friction force is increasing with the same amount that you are pushing the external force. Now, once you start moving, then Fa is larger than Fk. And now we have, instead of Fm, the friction, static, we have now kinetic. And the force is larger because the object is moving to the right side. Make sense? And that's the picture that Alyssa mentioned, that it said your static friction is larger at the moment of motion, about to move, is larger than the kinetic. Make sense with these? For static bodies, the magnitude of friction force is equal to that of applied force. For dynamic bodies, the magnitude of the friction force remains at a constant level. And see, it was increasing before movement, and then it's constant all the way when it starts moving, when it's dynamic movement, below the maximum static friction. Good. So let's do a quiz. Don't look at your notes. Can you solve this one? So you have a 10-pound block in equilibrium, right? And what is the magnitude of the friction force between the block and the surface? Your free body diagram, you can say that this is 10 pounds, right? So what would you do? What is your friction force? 2. Why? Yes. So now, because I told you it's at equilibrium, I didn't say that it's going to start to move or about to move. So I can't use the F equals mu n. If you do that, you can say that F is 0.3, the mu multiplied by 10, that's 3. But that's wrong, because I didn't say that it's about to move. If it's at equilibrium, you will say the summation of forces. So the friction, we have friction there. That's F, right? Summation of forces on the X equals to 0. So that's 2 minus F equals to 0. And F equals to 2. I need to, if you want to use Fs, I have to explicitly say it's about to move. Make sense? Okay, another question. The ladder AB is positioned as shown. What is the direction of the friction force? At B. It's going up, right? So this is going to move this way, so the friction is that way. This one is going to move down, so the friction is going up. So that's Fr. Make sense with these? Cool. Now, bodies in contact. Now, this is the thing that biomechanics. We would like to study when things are actually contacting each other. If you're an athlete, if you're looking at any, instrument when you play sports, the most important thing is that there is some contact taking or happening during this these interventions. And we would like to study that. So it's easier to pull or push a desk across the room. Which is easier, to push it or to pull it? Pulling is always easier. Always. Let me show you why. If you that's we talk about contact, right? We're contacting something. Now look at this. If you are pushing like this, you resolve this force, you will have one in the x-axis and one in the y-axis, correct? Now this force, if you want to do the equilibrium in the y-axis, if you stay on the surface, summation of forces on the y-axis should equal to 0, right? Is that correct? Now, the weight, so in order to have this at equilibrium, you have this force and you have that force need to be adding to get your reaction force. So you're trying to push something that is heavy with its weight, and also you're pushing down on it. So you're hurting actually your work this way. Alyssa, right? There is another force that you are adding down that is adding to the weight. So the reaction force going up now is two things. You need to account for those. Now, on the other hand, if you have this force, X and Y, you're actually taking subtracting. So the reaction force is smaller, and then it's easier for you to pull. That's not going to make any difference. They'll be the same. They'll be the same. But if you're trying to push from this with an angle, pushing this way is really, really making it hard for us to do that. And that's one of the things that people actually get injured because of it. Now, as we said, the coefficient of friction is something that you as an engineer, as a biomedical engineer, need to identify actually for a lot of variables. And that's important between the dancer. Let's say this is dancing or a dancer. So the shoes and the floor the friction should be small to allow mobility, but it should be also high in order not to the dancer to slip. Make sense? So that identifying the coefficient of friction for anything, remember, the shoe, do you remember how we define a biomedical device or instrument? It's an instrument that interacts with a biological living system. The shoes is actually a medical instrument. It's a medical device because it's interacting with the foot, and that deciding performance or the possibility of slipping or doing sliding. Okay, let's try to solve a problem. Now, without looking at your notes, I'm going to give you pieces of paper and see if you can solve this problem. Yeah, so let's say now this is a preparation also for the exam. And let's see if we can get it right. So you have a coefficient of static friction between a sled and the snow, 0.18, and the kinetic friction is 0.15. We have a 250 newtons is a force, right? So it's not kilograms, not mass. And the sled is 200 newtons. How much force parallel to the horizon surface is required to start the sled in motion to start? That's important. And how much force is required to keep it moving? So because I said to start, that is static, right? That's about to move. So let's see if you can get the values. And you can see the answers, but try, make sure that the key is the starting to move and required to continue moving. And you want to see which one is bigger. You got it? Any luck? Yeah, we're good with that? Any numbers yet? No? Okay. So because we're going to add let's say you're going to add the weight of the subject and the weight of the sled together, right? That's going to, so let's say this is the subject and the sled on top of it. So your force down is going to be the addition of the weights. So 250 plus 200, that's 450, correct? Newton, right? And I have about to move, when we are about to move, we have a friction force, and that's Fs. So assuming that the movement is on that direction, right? Correct? Fs is going to be the other direction, backward. But here's the thing. We said it's about to move. So we can use the formula Fs equals the mu multiplied by the reaction force. Now, my reaction force, in order to allow, that's the weight going down, R should be up, right? We don't have any movement in the y-axis. Summation of forces on the y should equal to 0. So if up is positive, 450, that's negative, right? So R minus 450 equals to 0. So our reaction force is 450 newtons. You multiply it by mu s, because I told you it's about to move. So how much is because required to start the sled in motion. You multiply which one? This is the Fs, right? 0.18 multiplied by 450, that's going to give you 81 newtons. This is the minimum force to start moving. That's the minimum. That's about to move. You're almost there. We're almost moving. Now, for the other one, we are already where we started moving, right? You remember we said that the force will be constant after you start moving. The friction force is going to always be constant. And it is the multiplication of the reaction force multiplied by the coefficient of friction, the kinetic coefficient of friction. So it's going to still, my reaction force is going to still 450, but you multiply it by 0.15 now. Does it make sense? Yeah. And in the exam, if I have one of these questions, I will ask from you to draw the free body diagram. Yes. In order to identify where the directions of the forces, the friction force. Make sense? Now, what would happen if I told you there is a wind that is pushing back on the subject with 4 newtons? Is it going to affect any of this? Is it going to affect our friction force? So we care about the reaction force up and down. If I told you that there is wind pushing this way, it's in the still horizon, right? So I'm not affecting anything going up and down. Your data will stay the same. Your friction force will be the same. It will slow the speed, but the friction force will be the same. But not the friction force. Because we don't have anything that affects the going up and down, right? The only thing that's going to make an effect, let's say one of them, if the boy is, wearing a backpack with 20 newtons now, that's going to affect your friction force. Make sense? Yeah. Okay. Yeah. These are the things that we are thinking about, and also when you're playing sports. So yeah, that is very important actually to analyze or to think about friction when any athlete is playing sports, and then the coefficient of friction of your wearables are really important in swimming and in let's say track and sprinting and other things. Okay. Any questions about the friction? The key word here is to start to slide on the motion. Means that we use the static friction, coefficient of friction. Okay, now, again, we're still studying bodies in contact. That's important for us in biomechanics. That's different from statics. So we have a new friction force called rolling friction. Have you heard about this before? Now, this is important for us, the rolling friction. So you have static friction. It's still a force. You have static friction, kinetic friction. The rolling friction is between two rolling objects and between a rolling object and a flat surface. Can you think of an example in the body? So, yeah, the socket joint, which is the hip, right? And here's the thing. This force depend. It's okay because the curvature and the flat surface of something. And one of them is big and one is small. So if you have a small ball and a big other, hold it. That is a little close to flat to that small ball, the other ball. Even we can look at the knees actually, that the knee joint is actually, when one is moving and the other one is not moving, you can approximate the tibia and fibula to be a flat surface for that joint. Now, here's the thing. Because it could be curved and a flat surface, and the surface are slightly deformed because of that movement, and it's influenced by the weight, radius, deformability. Why do you think what is the thing that add to deformability in our joints? The stiffer the bone, the less deformable. But the cartilage in the joints is deformable because it's soft, right? Now, this cartilage, when you move, actually, we are creating a friction force that can, create some clinical problems for us. Now, because the cartilage is soft and because it's deformable a little bit, we can get that, mechanical behavior and the coefficient of friction between the two surfaces. Now, here's the thing, guys. If you are interested in grad school, till now, we are unable to identify the coefficient of friction for cartilage and bone. Till now, we have no way or experiment to do that. In its structure. Let's say you worked for Stryker, a company that makes total hip and joint replacements. One of the things that you need to do is that for different materials, you need to have the coefficient of friction. So if you're using titanium, cobalt, chromium alloys, or any different alloys, the coefficient of friction is important to identify. And we're going to do this experiment on Thursday to identify the coefficient of friction. I want you to relate. So this is rolling friction different from the statics and that, kinetic frictions. But keep that in mind when you look at biological tissue. It's really important. Okay, momentum. You remember we talked about something called the torque, the moment. It's force multiplied by the d. So I would like to stop calling it moment so that we don't confuse ourselves with momentum. Call it torque. That's torque. Now, momentum is defined as a quantity of motion possessed by a body and measured as the product of the body mass with the velocity. Moment or torque, it was force multiplied by distance, right? Momentum relate to velocity. You play sports. You would like to move as quickly as possible, right? And that is related to momentum, which is mass and velocity, not force and distance. Does that make sense with us? Okay, so quickly, what do we have? The formula is moment, capital M, right? P equals mass time velocity. Sometimes people use P for momentum, but we will use M. Either way, it should be fine with you guys. Now, what are the principles of conservation of momentum? The momentum before should be equal to momentum after if we don't have any other influencing forces. So, in the absence of external forces, the total momentum of a given system remains constant before and after, and that's important in collision. right? And that, so remember, mass multiplied by velocity. Can you think of an example in sport that this could be actually a dangerous or powerful thing? Yeah. So how as you go to the, especially in football, right? American football, the mass is very important, and then you have the speed, and then you just unstoppable actually for that. Does that make sense? And we would like to assess that and make sure that we know what that is. So the mass before equals the mass after, because if you have someone with just a little bit slight of mass, difference in mass, you will have more momentum, and then they can push the subject away. Does it make sense? The slightest change in mass or difference in mass, bigger mass. And that's why teams try to make sure that, what do you call the front line? No, when you have heavy people. Yeah, the one that would protect the other guy. That's what you call. Yeah. So they pick them actually really, really, with heavy masses just to do that, to make sure that we don't do it. And so mass multiplied by velocity before equals mass multiplied by velocity after, and that's conservation of momentum. What affect change momentum? We have something called impulse, the product of force and time interval over which the force act actually. Now, remember when we talked about the impulse for the vertical jump, right? We want to link it to momentum, to speed. See, when you jump up, right? Impulse is actually something that produces a force a short period of time. Remember I told you that the impulse is important for ACL tears? What is the risk factor here? What is the thing that is going to add to the risk factor? It's not just the momentum itself, the impulse. It's the speed that someone is jumping up is actually adding to the ACL tears. So remember we said sudden changes, speeds actually can correlate to high risk factors, and including the impulse. The impulse is an indirect measurement of the momentum, of the speed. Does it make sense? That's why we like to calculate the momentum from ground reaction forces. Because if you want to measure the speed, you need to have pictures and using Kenovia and other things. But because we have the ground reaction forces, we can correlate impulse to momentum and then to speed. Does it make sense? Have a look at that. So that's change. What affect change in momentum? Impulse affect the change in momentum, and impulse is the force multiplied by time. Remember we had the area under the curve of the force in the ground reaction force. It's the area under the curve, which is force multiplied by the time intervals. That's what we did. That's impulse. So what is torque? The formula. Yes, force. Yes. What is momentum and impulse? Time. These are the things that we'd like. Those are kinetic variables for us to address. Now, impulse and momentum. The impulse is the change in momentum. The higher the impulse, what does that mean? The higher the change in momentum. Does that make sense? The higher the impulse, you remember the value that we measured, we said that could relate to ACL tears. The higher the impulse, the higher the change in momentum. Now, it means that you have zero, velocity, and then suddenly you're on higher velocity. That's a risk factor for ACL tears. And that's the same thing when we did with someone stopping or doing the crossing between, from one direction to another direction. It's the change in velocity that matters. Does it make sense with that thing? So impulse is the change in momentum. So the area under the curve that we calculated for the vertical jump is actually the change in momentum. And that's mv2 minus mv1, which is mass multiplied velocity after minus mass multiplied velocity before. And these are the forces similar to what we discussed before. What does the area under the curve represent? That's the impulse, right? Higher impulse means that the change in momentum is higher, which means that could be a risk factor for ACL tears. First time histories for high and low vertical jump by the same performer. Remember when we did the higher jumps, right? The impulse should be higher, which means the change in momentum was higher. That's a risk factor for ACL tears to get that. The shear area represents the impulse generated by the against the floor during the jump, and that's how you look at it. Remember this graph, right? The dashed line is the weight. This is preparing to jump and to call it. So we say the vertical ground reaction force, GRF, for a classic counter movement vertical jump illustrates peak force during, the propulsive push-off phase. Do you know which one is that? This is it. Make sense? Now, the area under the curve for this one, between the line and the weight, is the propulsive push-off phase, which is approximately, that's 1.4 seconds, and that represents the change in the impulse, which is the change in momentum. And peak force during landing phase. So we have two things for the vertical jump to assess: the area and this point. See this point here? The maximum force, landing force, is actually another risk factor for ACL tears, which is 2 seconds. The horizontal dashed line represents the magnitude of the body weight. If you have 725 newtons, how many pounds is the weight of the subject? You can convert it. You can, converting pounds and newtons. How many pounds would be that subject? 162.9. See? So you can find this information. The dashed area represents the ground takeoff. Yep, we're good with that. Now, impact, it's a collision characterized by the exchange of large force during a small time interval, right? So that's impact. Again, we're talking about bodies in contact. Sports, that's what we care about in biomechanics. Now, here's the thing. We have, how would a subject behave following an impact? It depends on the collective momentum and the nature of the impact. Do you know the plastic and elastic collisions? 100 elastic or plastic. So these are things that we need to look at. So perfectly elastic impact results in the conservation of the velocity of the system, impact of superpole with hard surface, and the perfectly plastic result in the total loss of the velocity. And you have, let's say, modeling clay dropped on the surface that loses the velocity. Let's do an example. On the same paper that you have, can you find for a 90 kilogram hockey player traveling with a velocity of 6 meters per second collide with an 80 kilogram player traveling 7 meters per second? If the two players entangled, so entangled means plastic collision, right? It's one object now, and continue traveling together as a unit following the collision, what is their combined velocity? So let's think about it for a couple of minutes and then we'll do it together. We need the velocity after the collision. Remember, we have conservation of momentum. Yeah, we will follow so mass 1 multiplied by velocity 1 plus mass 2 multiplied by velocity 2 before should equal the masses multiplied by the velocity after. Right? That's the conservation of momentum. And here's the thing. Which way do you think? Do you think the 90 kilogram guy with 6 meters per second will be able to push the 80 kilogram traveling 7 meters per second? How much is the difference in football? How much space is between the two teams when they start? No. So they're not going to be, catching up velocities, because one of the velocity is a vector. One of them right and one left. You need to have one positive and one negative. Okay, let me show you something. So if we did this, if I want to do that, let's see if that's going to be correct with the calculations. So if I assume, which way do you assume the 90 kilogram guy moving? So to the right or left? So that's going 90, right? That's kilograms. And then the velocity is 6 meters per second, right? The other guy is going the opposite direction. That's 80 kilograms. That should be bigger. And it is negative 7 meters per second, right? So summation of momentum before collision should equal to the summation of momentum after collision. So mass 1 is mass 1 V1 0 plus mass 2 V2 0 should equal, because they got entangled, it's m mass 1 plus mass 2 multiplied by the velocity after. Now, mass 1 is 90, the velocity is 6 positive, plus mass 2 is 80, and the velocity is minus 7, because velocity is a directional vector. And then you will have the two masses, 80, 90, that's 170, multiplied by v that I don't know. How many unknowns do I have? 1. You do the calculations and you find the velocity. And if you do that, let me erase this and show you the result. Here, that goes there. You will have minus 20 kilogram, 170. So the velocity is 0.12 meters per second, but it's a negative. What does that mean? A negative. It means that you go in the other opposite. So the guy with 80 kilogram, but faster, was able to push the 90 kilogram actually fellow. That's slower. And that's what I meant when we need to look at the small changes in velocities and masses. Does it make sense? We're good? Okay, now the same thing, this is, what do you call this? This is totally plastic collision, right? Analysis. Now, if you have elastic collisions, like billiards game, the break of the cue ball is strike to impact the high velocity, since the number ball are motionless, you want to transfer the movement to the other one, which is the momentum, right, problem. Do you play billiards? Do you know how to play that game? Cool. Now, let me show you. We're going to do an exercise. And the exercise needs from us to go into your computers and to do use as website. So any questions so far about this? We good? So let me close